Hi again, everybody, and welcome back. This is this is homework 7.4, and it's going to be problem number 1. And you might say that the same principles we use to solve 1 are also going to apply to problem number 2, even though I'm not going to do that one in this video. But the same idea applies right here. All right. So this homework problem set is called kinetic and static friction. All right, because we need to determine if kinetic friction is going to come into play or if static friction is going to come into play. So what's happening here is this. We have a box on a ramp, okay, and it has a certain, where is it? It's got a certain weight, 45 newtons, all right? So we can say that the weight, that should be straight down right there. Let's try that again. The weight force, mg, still not very good, sorry, equals 45 newtons. So you should also be able to divide that by 9.81 and get the actual mass, even though I don't think you'll need that right off the bat. So what's happening here is this. This block inherently has a weight, and therefore it has a, on that inclined plane, it has a force parallel and it has a force perpendicular, right, that you guys all know. Perpendicular. You guys all know how to calculate. It also has a normal force directed upwards, like so. And there's going to be some sort of friction force. In fact, I'm going to make that a different color. I'll make that brown. That is acting against the direction of motion. All right. I'm not going to call it Fs. I'm not going to call it Fk either. Oh, by the way, right here, that should say mu sub s, not x. Sorry, so that little tiny thing should be an s right there. The s is right next to the x on a keyboard, so that was a typo. So I don't know if it's going to be static friction or kinetic friction, because I don't know yet if it's going to be moving or not. Because here's what's going on. We have all the forces that are associated with an object on a ramp, but this force P that is different in parts A, B, and C right here, this force P is another added force acting down the ramp. So first we need to find out, is it going to move at all? And then what we need to find out is what kind of friction is acting against it. Is it static or is it kinetic? And what is the magnitude of that friction? All right. So for part A, right here, I'm going to redraw. I'm going to redraw this slightly, and there's our ramp right there, and we have our theta, which is 15. Okay. In fact, I'm not going to redraw that. I think it's okay the way I had it, at least initially. I may need to redraw it for one of the other parts. So, the net force in the x direction, what is it? All right, so this is A right here. Well, it's going to be the force. I'm sorry, did I say the x direction? Net force in the parallel direction, right? The net force that is along the face of the ramp is going to be what? It's going to be the force parallel, because that's acting down the ramp. And by the way, I'm calling the down direction positive. I'm just calling it that. What else is acting in the same direction? Well, P, right? P is acting in the same direction, but that friction force is acting against it. All right, so initially this is at rest right here. So the question is, what is the maximum static friction force? Now remember, friction only acts enough as it has to, but static friction force has a limit. Now, there's a maximum static friction force that can be applied between any two objects, and if you overcome the friction, it's not going to be static anymore, it's going to start moving. So let's find out what that is. All right, static friction max is what? Well, that's the mu s, which that was the typo, times the normal force, right? Well, we can write that out in more detail. It's going to be mu s times the normal force, or the force perpendicular, which is mg cosine theta, right? And you knew that. That's an end parentheses right there, sorry. Cosine theta. Okay? So what is going to be our Fs max right here? Well, we have our mu s, and that is, it looks like it says mu x, but it's mu s 0.50 times what is our mg cosine theta. Looks like our mg cosine theta is going to be 45 times a cosine of 15 degrees. All right, what do we get as the maximum static friction force? Times 45 cosine 15, 21.7 newtons. All right, let's dotted line box that. What does that mean right there? Well, because of the normal force acting between the box and the ramp, and because of the static friction force, it will not move. That is, it will be able to withstand a downhill pull of up to 21.7 newtons. You might say there's 21.7 newtons of static friction available to counteract the downward pull of the downward parallel to the ramp pull of the force parallel and the P force right here. Okay, so let's find out what that actually is going to be. What's the net force in the? Or sorry, let's just say. So for the moving force, I'll call it moving force. Well, okay, so we've got force parallel plus P, right? So that is that's mg sine theta plus in part A it's I should put a plus in there, right? In part A it's 5 newtons. I should have just written in the values. So that's 45, sine 15 plus 5 newtons, right? Because you're pulling downhill with that 5 Newton P force right there. So what does that add up to? I get that it adds up to 16.6 newtons. All right? So here's what this means. There's 16.6 newtons of force trying to move it downhill. That's the P, and it's the force parallel, right? But because of the coefficient of static friction and because of the normal force that is naturally applied into the ramp because of the weight of it, there is up to 21.7 newtons of static friction. So the question is it going to move or is it going to not move? And the answer is no. It's going to not move. No motion. Because that is greater than the downhill parallel force. All right. But the question is asking is, what is find the magnitude and direction of the frictional force acting on the block. All right. Well, remember friction. Even though we have up to 21.7 newtons of static friction force, it only needs to provide how much friction? Only that much. So the static friction force, I think I was writing that in brown, wasn't I? Static friction force that is acting on this block right here is going to have to be 16.6 newtons, and that's our answer for part A. All right. You're going to do the same thing for part B. Now, part B and part C, that downward pull, that P force is going to be greater, and so it's like you're pulling downhill greater. So at some point, my guess is we're going to overcome the maximum static friction force, and it'll turn into kinetic friction. In which case, we'll have to figure out what the kinetic friction is. But for part A, we can say that, okay, there's more than enough available static friction to prevent it from moving, because this is the only force trying to move it downhill. And so we can say, all right, well, the static friction is going to be exactly equal to this right here, because friction only provides as much friction force as it needs to, at least static, as it needs to prevent motion. Okay? So that's part A right there. I'll do part B. In fact, no, I won't do part B. I'll let you work that out, I think, but the principle is going to be the same. All right? We've already determined the maximum static friction force. The question is the downhill forces going to be greater than or equal to this? less than or greater than equal to this. If they're less than it's going to remain stationary, and it's only going to provide enough force to counteract the downhill forces. If the downhill forces do cause it to move, then you no longer have static friction, but you have kinetic friction, and you need to calculate the kinetic friction that way. All right, so that's the principle. I'm not going to solve B and C for you, but I think that should lay the groundwork for you to be able to do that yourself. So again, if you have any questions, please make sure you see me. But in the meantime, thanks for watching, and I'll see you on the next one.